Hello everyone, myself Upasana Sharma. Today I am going to discuss about the flip-flop applications. So we have two types of applications that I am explaining here. One is counter, another is shift register. So in this video I will be explaining the counters. So counters are the registers capable of counting the number of clock pulses arriving at the input of the flip-flops. And shift registers are used to store the bits in the flip-flops. So counters are used to count the clock pulses which have arrived at the input of the flip-flop. These are the counters. Counters, we have two type of counters. One is asynchronous counter and another is synchronous counter. Asynchronous counter and another is synchronous counter. Asynchronous counters are those counters in which we give the clock pulse at the first flip-flop. Suppose I'm making here 2-bit asynchronous counter. Asynchronous counters are also called as ripple counter. In asynchronous counter, the clock pulse, we give the clock pulse at the first of the flip-flop clock. This is first flip-flop. Suppose we are making this counter using the JK flip-flop. This is J1, K1, and output is Q1. J2, K2, output is Q1. तो फर्स्ट फ्लिप फ्लॉप को हम क्लॉक पल्स देते हैं and the output of first flip flop goes to the clock of second clock pulse. The input J1 K1 is connected to the logic 1 and this J2 K2 is also connected to logic 1. We have two outputs Q1 and Q2. So this is the asynchronous counter in which we give the clock pulse only for the first flip and the output of first flip-flop is connected to the clock pulse of the second flip-flop. Now, in synchronous counter, if we are making 2-bit synchronous counter, in synchronous counter, we give the clock pulse to all the flip-flops. This is J1, K1, output is Q1, J2, K2, output is Q. We give clock pulse simultaneously to all the flip-flops. Q1 connected to the J2 and K2 and J1 K1 is connected to logic. So this is the synchronous counter. In asynchronous counter, we find the ripples at every output of the flip-flop. But in synchronous counter, all the flip-flops work simultaneously, so we do not find any ripples at the output of any flip-flop. Synchronous counters are faster than the asynchronous. This is the difference between the synchronous and asynchronous count. We will design a asynchronous and synchronous counter. So in asynchronous counter, suppose we are discussing here first asynchronous counter. Suppose we have a n number of flip-flops. That means the total number of states that will be counted by the flip-flops are total number of states equals to 2 to the power n. Suppose we have a 3 flip-flops. That means the total number of states will be 2 to the power 3 equals to 8. Or we can say 0 to 7 states. If I want to make a BCD counter, BCD counter counts, BCD means 10 states, 0 to 9. So 10 states. So that means we require a 4 flip-flops, in which 4 flip-flops means we have n equals to 4. So that means total number of states would be 2 to the power 4 equals to 16. So that means हेलो हाँ मैम हाँ आयु वीडियो बना रही थी जरा लंच हाँ करते हैं एक ही वीडियो खत्म कर लूँ ये वाली आप इतने गर्म करके आओ मैं गर्म करके पहुंचती हूँ है ना इस वीडियो खत्म करके आती हूँ है ना पॉज की हुई है हाँ हाँ हाँ, ठीक है So that means 0 to 9 total 10 axes will be used but 10 to 15 states will not be used. So these states are unused. So for designing a BCD counter, we require 4 flip-flops. Now, suppose we are designing here 3-bit asynchronous counter. For 3-bit asynchronous counter, for 3-bit asynchronous counter, 3-bit asynchronous counter means n equals to 3 and total number of states would be 2 to the power n equals to 2 to the power 3 equals to 8. That means 0 to 7. So 3-bit asynchronous counter counts the total 8 states. So in 3-bit asynchronous counter, we require 3 flip-flops. 3-bit means 3 flip-flops. And first flip-flop input is J1, K1. Output is Q1. Second flip-flop inputs are J2, K2. Output is Q2. And third flip-flop inputs are J3, K3. And output is Q. In asynchronous counter, we give the clock pulse at the first flip-flop. And the output of first flip-flop gives to the clock of second clock pulse. And this Q2 connected to the pulse of third flip-flop. And all the inputs are connected to the logic 1. This is right. This is the 3-bit asynchronous counter. We will take outputs from this Q1, Q2, and this third one is Q3. That if I want to see the table of this 3-bit asynchronous counter, we first take the Q3, then Q2 and Q1. It will count from 0000001, 010, 011, 100, 101, 110, and 111. This is the table, truth table that this 3-bit counter, right? If I want to see the state diagram of this 3-bit asynchronous counter, they are 000, 001, 210, 11, 00, 01, 10, this is also called the up counting. That means it counts from 000 to 111, low to high. This phenomena is called the up counting. Okay, this is the 3-bit asynchronous. Now, we are making 3-bit synchronous counter. Now, making the 3-bit synchronous counter, 3-bit synchronous counter, same, we require 3 flip-flops. But for designing the 3-bit synchronous counter, first we have to design the table, 3-bit table for synchronous counter. So for 3-bit table, we have outputs Q3, Q2, Q1. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0 and 3-bit सिंक्रोनस काउंटर को बनाने के लिए हमें जिस फ्लिप फ्लॉप से बनाना है उसकी हमें आउटपुट्स इनपुट्स लेनी पड़ेंगे. फॉर एग्जांपल वी आर मेकिंग 3-bit synchronous counter with the help of T flip flop. For Q3 we have T3, for Q2 we have T2, and for Q1 we have T1. Now we use the excitation table of T flip. Excitation table, we know for excitation table we have QT plus 1, and we are making with the help of T flip flop. So this is the T, and for this we have 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0. This is the excitation table of T flip flop. Now हम यहाँ पर आते हैं. If Q3 present state of Q3 is 0 and next state is 0. For 0, 0, for 0, 0 we have the T0. That means this will be 0. For 0, 0, same 0. Again 0, 0, 0, 0, 1. For 0, 1 it is 1. अब इस तरह से यहाँ पर अब यहाँ 1, 1, 1 है तो लास्ट वैल्यू है 0, 0, 0 because after counting this 1, 1, 1 this will again go to 0, 0, 0. So इस हम इसी तरह से बना लेंगे इसकी with the help of excitation table. Then हम क्या करते हैं इसके बाद we draw the KMF for T3, T2 and T1. Here we make the KMF for T3, T2 and T1. So for T3 we find the output that is equals to Q2 and K1. And for T3 it will be Q2. For T2 it would be Q1, and for T1 it would be only 1. So हम इस तरह से कनेक्ट कर लेंगे J1, K1, J2, K2, J3. J1, K1, first of all the clock pulses are connected simultaneously. This is synchronous counter. And J1, K1 is connected to logic 1, and this is, sorry, we are making here with the help of T flip-flop. This is T, not JK, this is T. T, T, T flip-flop. This is T. So this is Q1, this is Q2, and this is, and T1 is 1. That means T1 is connected to logic 1. T2 is Q1. So T2, this T2 is connected to Q1. Q1. And the output हो गया हमारा, this is Q1, this is Q2, and this is Q3. And this T2 is Q1, we have connected here, and T3 is Q2, Q1. T3 is Q2, Q1, that means this Q2, we use the one NAND gate, AND gate, Q1 and Q2 and connected to. This is the 3-bit synchronous counter using the T flip-flop. These are the references. Thank you.